Energy. What is energy and how do we measure it? If you pick up any high school textbook on physics and you look for the definition of energy, what you'll see is that energy is the ability to do work. But if you look in the same book and you look up a definition of work, what it'll say is that work is a transfer of energy. And you soon realize that we are really no further along in understanding what energy is. So why is energy so hard to define? Energy is what is known as a fundamental property. If you have any concept and you're trying to explain it, you do that in terms of simpler concepts. And in turn, if you want to explain those simpler concepts, you explain them in yet simpler concepts. But eventually, you reach some concepts which are so basic that you must experience them to understand them. You just cannot describe them in simpler terms. So other examples of this would be mass. The fact that matter exists is something so fundamental that you have to experience it with your own senses. You cannot really explain that to somebody else. Volume is another fundamental property. The fact that matter occupies space is something that you have to experience yourself. How do we measure a fundamental property? Let's start by talking about how do we measure mass. Now, we cannot measure mass directly. There's no such thing as a mass meter. What we do is we measure its weight. The weight is the force exerted on the body by gravity, so we can measure that force. And we can also measure the acceleration produced by gravity. The mass is the ratio of this force to the acceleration due to gravity. Now, this has given us a measurement of mass, but we still don't have a definition of mass. We are going to measure energy in precisely the same way. So a system possesses energy if it can lift a weight. The amount of energy it has is measured by the height that it lifts the weight. We will never give a precise definition of energy, but we will have a way of measuring it. We have a stone block which is sitting on a table, and we want to know whether it possesses energy. We can use a pulley and a rope to connect it to a mass, and this is a known mass. We would then see if we can lift this mass. So we remove the table, the stone falls down, and it lifts the mass. And we can measure the height by which it lifts the mass. So how much has the energy of this mass m increased? The force which is lifting it is equal to m times g, and it's lifted it through a height delta z. So the work done on the mass is the force times the distance, which is mg delta z. We call this the increase in the potential energy of the mass. The work done in lifting the mass in a gravitational field is stored therefore as an increase in its potential energy. If we have a moving object, does it possess energy? We can test this by building some apparatus which we can use the motion of the object to lift a weight. So as it flies through, it rotates the pulley and the weight is lifted through some height. And therefore, this will give us an indication of how much energy the object had. We can also calculate that when the velocity of the mass m changes, we can calculate how much its energy changes. So this is a mass m, which is at a position x1, and it has a velocity v1. If it's accelerating, there must be a force F acting on it. And as the mass m moves at a position x2, we say it has a velocity v2. So the force accelerates the mass from velocity v1 to v2. The work done by the force therefore increases the energy of the mass m. We can find out how much work this is by integrating f dx from x1 to x2. The force F we know is the mass times the acceleration. And since the mass m is constant, we can take it outside the integral. Now to evaluate this integral, we need a relationship between the acceleration a and the displacement x. We know that the acceleration is dv by dt, the rate of change of velocity. We can use the chain rule to write that as dv by dx times dx by dt. But dx by dt we know is the velocity. So we can write this as dv by dx times v. Let's take this definition of acceleration and put it into our integral. So now the work W is m times the integral of v dv by dx times dx. Dx cancels out and our integral becomes m integral of v dv. And this we can evaluate easily and it becomes m half v2 square minus half v1 square. This is the work done in accelerating the mass m from velocity v1 to v2. Let us define, therefore, a new type of energy, which we'll call the kinetic energy. And this is defined as being half mv square, where v is the velocity. So if the velocity changes, the change in the kinetic energy, delta Ke, is half mv2 square minus half mv1 square. The work done in accelerating the mass is stored, therefore, as an increase in its kinetic energy. Heat is also a transfer of energy because we can use heat to raise a weight. We do that by taking a cylinder filled with gas, and on the piston we can place the mass which has to be raised. Now we heat the gas expands and it lifts up the weight. If we want to analyze this, we are transferring energy in the form of heat to the gas. And the energy of the gas therefore changes. And the gas then does work on the mass. The heat therefore is increasing the energy of the gas. The question is, what is the form of energy which is in the gas? It's not kinetic energy because the gas is not moving. It's not potential energy because the gas has not moved in its position. The energy stored in the gas is a microscopic form of energy. And energy can be stored in microscopic forms at the molecular level. So these don't require a change in position or velocity of the system. All these microscopic forms will be known as internal energy. And the changes in internal energy typically correspond to changes in either temperature and pressure. So what sort of microscopic forms do we have? First, we got molecular motion. So molecules move at random, and we have energy stored in their kinetic energy. We also have molecular spin. So if we have multiple atoms in a molecule, they spin, and the angular kinetic energy is another way of storing energy. We have molecular vibrations. As the atoms in a molecule vibrate, there's energy stored in this motion. And finally, we have chemical bonds. There's energy stored in the chemical bonds between atoms in a molecule. Now, we are not going to worry about all of these different forms of energy. We will simply lump them all together and call them all internal energy, which will include all the microscopic forms of energy. The total energy of a system therefore includes the macroscopic forms of energy, which correspond to a change in position or velocity of the system. These include the potential energy and the kinetic energy. Microscopic forms of energy are those that correspond to a change in temperature or pressure of the system, but they don't require a change in position or velocity. We add all of these together and we call that the internal energy. The total energy of a system, therefore, is the sum of the potential energy, the kinetic energy, and the internal energy. To summarize, energy is a fundamental property that cannot be defined in simpler terms. A system possesses energy if it can lift a weight. The potential energy depends on the position of a system. The kinetic energy depends on the velocity of a system. The internal energy, the sum of all the microscopic energy in a system. And the total energy, E, is the sum of the potential energy, the kinetic energy, and the internal energy.